All right, we're gonna look at a weak acid, strong base titration where we left off in class, which was E. We have 50, we're adding 50 mils of a 0.1 molar solution NaOH to our same acid solution, or to acetic acid, which was 0.1 molar acetic acid. And that was also 50 mils. Okay, and that Ka was 1.8 times 10 to the negative 5. All right, so looking at this point, right, when we write out our first equation of what's going on here, we have our acetic acid, C2H3O2, is going to interact with that strong base proton ion, or sorry, hydroxide ion. We're going to create the acetate ion plus water. Okay, sure we can see all that. Okay, and looking at this, right, we need to do our before and after. So, right, not initially, but before our reaction takes place, we have 0.1 molar times 50 mils, which would be 5 millimoles. And our hydroxide is also 5 millimoles, okay? And when we go to subtract for the after, right, they're both going to be consumed because we have 5, so it doesn't matter which one we choose, but they're all going to disappear. We're not going to have any of this left over. But remember, don't forget we're adding. So we do have 5 millimoles of acetate ion left. This is important, okay? So we have that left over. Okay, so if you think about it, in our solution, we have the Na still floating around. We have this acetate ion still floating around. And we have water. Well, we know the sodium's not going to do anything, so we have these two species floating around, which, right, are going to interact with one another. So we're going to have our base, our acetate ion, plus water. It's going to end up forming the acetic acid, and then that hydroxide constant, or ion. Okay, now looking at this, since we have remaining acetate ion left, we really have to look at what this ion is doing, right? And we can see when it interacts with water, it's acting as a base. So because this is acting as a base, we have to remember when we do use a chemical equilibrium expression that our K, we must use Kb, right? Because it's acting as a base. We have to use Kb. All right, so we're going to fill in our table. We know we have 5 millimoles of our acetate ion, fill in 5 millimoles. We're going to ignore water because it's a liquid. We don't have any of this yet. All right, then we're going to minus x plus x plus x. So at equilibrium, the expression should be 5 millimoles minus x, and then x and x, okay? So we need to solve for the Kb, because remember this is acting as a base, so we know Kb is 1.0 times 10 to the negative 14 over the Ka, which was given 1.8 times 10 to the negative 5, which gives us 5.6 times 10 to the negative 10. Okay, and we also know that this expression equals our acetic acid times hydroxide concentration all over our acetate ion. Okay, so we're going to plug in or what we know. So we have 5.6 times 10 to the negative 10 equals x squared over 5.0 millimoles. Don't forget this needs to be concentration, which I forgot to do up there. This is over 100 mils minus x. So really quick, I'm going to go back up here, right? We can't use this. This needs to be concentration, so in 100 mils. In 100 mils. Sorry, guys. Okay, we're going to ignore this x, and we get x, when we solve for everything, you're going to get x equals, or you should get 5.3 times 10 to the negative 6. Now this is important. This is our hydroxide concentration. Therefore, when you solve for the pH, you're really getting the POH is the negative log and then we get the POH equals 5.28. So 14 minus 5.28 gives us grand pH of 8.72. Okay, this is at equivalence due to the fact that at the very beginning of our problem, all of our acetic acid and all of our OH were used up, okay? So this is an at equivalence point problem for a weak acid strong base.